Good morning, Python people. Good morning. First up today, we've got Chenyang Wu. Chenyang Wu is a hacker, a programmer. He's currently working at Facebook and Instagram. He's worked on some low-level Python projects, loves playing with fancy and abstract features of languages, and is infamous as the GC killer, which I guess hopefully he'll talk about today. So please put your hands together for Chenyang Wu.
Hello, everyone. Thanks for coming. My name is Chenyang Wu. I'm a software engineer at Facebook and Instagram. If I'm famous for anything, I turned off the Python garbage collection at Instagram. If you came to Chris' talk yesterday, there's a link in his slides. But if you search for Instagram garbage collection, you can find our engineering blog there. But I'm not here to talk about that today, luckily. Today I'm here to tell you a story about how we enable hot reload on a large amount of servers, how that benefits us, and what are the lessons learned along the way. So here's the agenda of my talk. First, we'll go through why we're doing continuous deployment. We'll see a typical workflow of how the continuous deployment works. Then we'll go into details about how we can evaluate different options and choose one of them and actually make it work. And then we'll close with some conclusion, and hopefully we have time for questions. So as you might already know, Instagram loves continuous deployment. We have been doing CD. I'm just going to refer to it as CD from day one. And it's one of our key factors that enable us moving fast and ship the product that people love. So here's a link to a talk from one of my talented colleagues, Michael Gorman. It's called Continuous Deployment to Millions of Users 40 Times a Day. You can watch it from the link here below. Probably will get my slides after this. But basically, with continuous deployment, you will be able to act fast and find problems like exceptions or failures easily. And you will be able to pinpoint problems from certain commit. And you can collect user feedback faster. So the backstory here is, recently we were starting seeing some issues with our continuous deployment. But before we go into there, let's see how the system works. So assume you have a cluster of machines that you are serving the users, and you want to push a code change. So you click the big red button on your laptop, got push. So your deployment script will find certain machines. So we'll figure out a deployment speed, for example, 10%. So we'll just access it into a bunch of machines you have, and then copy your new code there, replace them, restart the server, and typically in our case, a restart on one server takes 15 to 20 seconds. So it repeatedly does this until all the servers are restarted. Then your new code is live. So two things to remember here is when you restart your server, first, you have to wait for the current user request to finish, because otherwise we will drop the user request. Second is you have to mark your server as down on your load balancer so that you don't have more requests coming in. So this approach is fine. It works really well. It serves Instagram well for at least 3 years. So what could possibly go wrong? So first one is apparently it's kind of slow. For continuous deployment to be continuous, it has at least to be fast. So the issue here is there's a linear correlation between how many servers you have and the time you take to get to all of them. So apparently if you have more servers, it means you just take longer to restart them. So this certainly does scale very well if as your company scales. Secondly, during deployment, for example, 10% is your deployment speed. Your server is basically down by 10%. So on one hand, when you do your capacity planning, figure out how many machines you're renting from AWS, you have to take this into consideration. So when you do that, you usually target for the peak time. And basically, in this case, the peak time, you just created it with your push. On the other hand, it also means you will see this regular jump on your utilization graph during your push. Basically, your system runs hot for several minutes because you have less resources to serve the users. So because the way it works, you have to coordinate among all the servers. Usually what you do is you take the deployment speed, convert it to server numbers, and then spread that number across all the clusters based on how many machines are there in the cluster. So this is like probably a tedious process. And it gets worse when you actually have an unbalanced layout across clusters, which is actually pretty common. The next reason is kind of rare, but think about if some of your clusters are down for whatever reason. So what you usually do is you shift the traffic to other clusters. At Facebook, we actually do this kind of regular drills. We call it storms by taking certain data centers down. So during these kind of events, what happens is your utilization will be much higher than usual. When you push your code, you have to move very, very slow, which is bad because you expect your engineers, especially your product engineers, to do their daily job even during these events. So this kind of thing basically amplifies what we talked about earlier about the scalability issue. So basically with the current approach, even though you're not downgrading your user experience, but in some cases, you either have to do that or you have to be very slow and careful. So the question here is, can we do better? The answer is, of course, yes. Otherwise, I won't be here. But the idea here is when you face a problem, it's actually often helpful to take a step back and think about it from scratch. So the goal here is we want to push your code without disturbing the users. The biggest assumption we were relying on with the old approach is the fact that you have a lot of servers. You are free to take some of them down. So if you only have one server, what do you do? It's actually pretty straightforward if you think about it. Just do not shut down the old server process. Just start a new server process that acts exactly the same way, wait for it to be ready, and then switch over. So instead of having two machines, in that case, you just have two server processes on the same machine, uses twice as the memory. So there are two questions we need to answer here. First, how do you have two server processes that behave the same way? Specifically, how do they bind to the same port? Secondly, how do you afford to run two servers on a single machine? So to understand them, we'll first go through how we run our web servers. Let's look inside. At Instagram, we use UWhiskey, and we use the master mode. So how many of you use UWhiskey, actually? Yeah, fair amount. OK. So the master process manages all the worker processes, and it's the one who binds to the HTTP port. So the biggest thing to notice here is these worker processes are created using a syscall called fork, which is the key point that enables these worker processes to share the same socket from the master. Then what happens is each of these worker processes will be able to accept a connection from the same socket and continue from there. So there are two modes running UWhiskey, which is pre-fork versus lazy app. So in pre-fork, master loads the app first, and then fork the workers. So what happens in this case is all the app memory is shared across all the workers. On the other hand, if you do lazy apps, master do not load the app, but each worker loads the app separately. So the difference here is that each worker will have a dedicated copy of the app memory. So there is a blog post about it, which I highly recommend reading through it. I got a lot of insights from it. We actually made the same choice in the end. But there is a measurement in this blog post that even the simple Hello World Django app, if you use lazy app, each worker takes about 15 megabytes of memory, which is pretty bad. So that's why I don't think we recommend using lazy app in production. So the next thing to talk about is there's a feature called reload on RSS in UWhiskey, which is if any of the worker uses too much memory, then let's get bigger. The master will see that and then tries to restart it. So it sends a signal, burns it, and then refork it. So this mechanism ensures you have a reasonable utilization of your memory. And it's actually pretty common if you run your servers as a reasonable high memory utilization because of this mechanism to fully leverage the resource you have on that machine. So when you start to think about it, you'll definitely find this wiki page from UWSG official doc called The Art of Graceful Reloading. So this page is very informative. I would highly recommend reading through it. But here, I'll just list a bunch of options that from this page, and we'll go through them one by one. So subscription system is pretty much like what we did before. It just you wish you added an extra layer before your master. But it still relies on you have a lot of servers. And it suffers from the same issues we had. So we have this Zerg mode thing, which is basically like you have another Nginx running on your server, and then you can just do whatever you want behind the scene. The reason we're not choosing this is having another server on your machine, because there's another layer of indirection, it probably adds latency. The other is having that server is another single point of failure. So these other options, we'll go through them using diagrams. With this chain reloading, it's under the assumption that you're using lazy app, but the idea is since you can reload your workers separately because they're independent from each other, when you reload them, you can just make them become the new code. As mentioned before, lazy app is not recommended because you cannot benefit from shared memory. But the reason we're putting here is the final approach we're taking is very similar to this one. Pretty much a batched version without the limitation that you have to do lazy app. So next option is SO reuse port, which basically removes the limitation that you can not bind to the same port from multiple processes if you have a newer enough Linux kernel. So here's a simple demonstration. If you set the option on your socket, you will be able to run multiple servers, and they will all bind to the same port. So the issue here is the motivation of the Linux implementation of this option is for job scheduling. So which means if you have multiple processes bind to the same port, a new connection comes in, the kernel will give this connection to either of them evenly, hopefully. So if you run this snippet on the Linux system, you will see you get random PIDs each time. So the problem here is if you try to shut down any of them at any time, you have to make sure there's no pending request in that process's listen queue. This could be really tricky because you wanted a CAS operation on a socket. Otherwise, you're still risking dropping user requests. So interestingly, in the BSD implementation of this, the kernel will actually give the connection to the last bound process. So if you run this on your MacBook, you will get the same PID every time. So there's the option called master fork. The doc says it's like black magic. But if you look at it, it's not that magical. So the idea is it applies the same trick that enabling both master and worker sharing the same socket. So we wanted it if you wanted to have a new process bind to the same port, you just fork from the old process that possessed that port and then start from there. So basically, it's really easy to get started with. UWSG has a thing called master FIFO, which is like a FIFO file where you can send control command to it. Just pipe an F to it, which means fork, and then it will just fork a new master. So in this case, a new master is forked, then we'll call execute on itself to load your new code, and then it will fork its own workers. So after this is done, you can get rid of the old masters and its workers. So of course, different people would choose different options, but we ended up picking master fork. The reason is, first, it's really easy to get started with, and it has minimal overhead compared to all these approaches, and the fact that it has no additional components, which means you don't have to maintain them. So now we just have to make it work. So the potential issues here include, first, because you have two masters behave exactly the same way, they will step on each other. Second is the memory overhead of running two sets of workers in memory is still an unsolved issue. And then we'll see later where the way we deal with the memory overhead is not fast enough, and then we will get it faster again. Oops. So because you have two masters with the exact same config, they will step on each other. For example, the master FIFO, when you pipe a lighter to it, you're not sure which master gets it. Or the stat socket where you can get stats from the master, they will be fighting over these kind of resources. So finding these kind of inconsistent state is easy. Just go through your UVC config files and find all the things that looks like resources, like files, sockets, stuff like that, and deal with them one by one. So with master FIFO, UVC provides a way to deal with it. The idea is you put multiple entries in your config, and then you will be able to change the active one by piping the ID. This is kind of weird, but it works. With other things like stats files, the way to deal with them is like actually just simply moving them. So the idea is, since you wouldn't close the file descriptor, if you move them, you will still be able to write to them. This also applies to things like PIT file that we don't use, but it's the same idea. We also set vacuum to false so that when you shut down a master, it wouldn't remove all these files. Otherwise, you're getting pretty messy. So to deal with the memory issue, what we do is pretty much similar to the chain reloading thing. So the idea is we make the new master starts with one worker, and then we slowly hand them over. So here's the demonstration. We start with the same setup. Your laptop comes in, and it pipes in 1F to the FIFO. So 1 means switch to slot 1 first. Otherwise, when your new master comes, they will fight over the slot 0. And then fork. So then the new master shows up after executing itself. Then we'll start with 1 worker. Then we'll pipe a minus sign to the old FIFO, which burns one of the old workers, and a plus sign to the new FIFO. So we keep going until all the workers are gone in the old master. Then we shut it down. Here is how the config looks like now. So basically, we enable this thing called cheaper mode, which allows you to control the number of workers via talking to the FIFO. When you set your algorithm to manual, it prevents you basically to do this kind of thing behind your back. Also, our script, which is a coordinator, locks the file when it starts. And in this config, we just look at the file, see whether it's locked, to tell whether there's a hot reload that is running. If there is, we're just going to start with 1 worker by setting the cheaper initial value here. So here is a simple demonstration of how it works. You basically have a for loop under each of this iteration. You tell the old master cheap 1, while after that was done, you just keep querying it, and then you tell the new master to spawn 1. So it seems like we got a working deployment, but the problem is it's really slow. So above is the old timing for the deployment, which is shutting down a server takes 15 seconds, start it takes 5. So restart is actually pretty similar to the master fork here because they're basically doing the same thing, but the master fork is slower because in this case, your server is actually serving user requests. So it's doing other stuff. Assume you have 60 workers in this case. If you look at the code we have, each iteration takes at least 1 second. So in this case, you're taking 60 seconds to hand over all the workers. So the bad part about it is related to how many workers you have. And if you look at the real timing, it's actually a lot longer. So we need to get it faster. So the way to tackle it is by batching. The idea is you can just move more workers if that's possible. the general thing we wanted to achieve is we wanted this deployment to be reactive, meaning if your machine is busy, we'll just move slower. If it's not, we'll just move faster. Here is the general workflow, like compared to before. So basically, we get all the stats, and then we calculate the several bounds to decide how fast we want to move. So first thing we look at is how many idle workers are there in the old master, because you cannot move faster than that. The other workers are busy. So then the memory bound is it takes into consideration of how many active or live workers running in the memory. So live means it's running or it's shutting down, because shutting down actually takes time, but forking a new one doesn't. So if you move too fast than this, you will have too many workers in the memory, which would potentially ruin the machine. The remaining bound is just like how many things you have left. Then we just take the minimum of these and then make a decision. So there's a bunch of things that needs to be fixed inside USG for this batching to work. So the first thing is, I'm pretty sure this is a bug, but if you pipe multiple minus sign to the FIFO, it will just not work because it will only take one. If you cannot see this clearly, this is just adding a while loop. So the next fix is highly related. After you fix the multiple chipping thing, you will see your chipping is actually not reliable, which means since we're only chipping idle workers, what happens is if your server is really, really busy, your chipping command is simply ignored. And the worst part of this is you don't have a feedback. You don't know whether the master is shutting down the worker or it's just like ignoring a command. So in order to not lose track, the idea here is if any of these operations fails, you just return the operation to the pool and retry it next time. So this fix and the previous one is in the same PR and has been merged. The next thing is exactly the opposite. So when your server is extremely idle and you by any chance enable this thunder lock option on your server, you will be in trouble. So the link here under the bottom describe in detail how, like, what is the problem that thunder lock is trying to solve. But the idea is thunder lock is a shared lock across all the workers. Before each worker tries to accept connection, we'll try to acquire this lock first. So the idea is thunder lock gives you fairness among all the workers. So the problem is acquiring a lock, this operation is not interruptible because internally it does retry. But USG relies on interrupt to wake a process up from syscall to chip it. So when you chip a worker that is actually blocking on the first line here, it would just not work. We're just stuck there forever and got killed after like 20 seconds, like however long you set your timeout is. So the fix here is fairly easy. Since we're also chipping, only chipping idle workers, you can just do SIG-hop instead of some random signal. But this hasn't been merged because this really has to want it to be made into an option, but you get the idea. So after the batching fix, if you look at the timing, it's actually getting a lot faster. Oops. So note that all these are artificial numbers. It totally depends on your config, but the difference here is the complexity was reduced from the number of workers to something that is more related to your load. Also, there's a lot of fine-tuning you can do beyond this if you wanted to make it perfect. Since we already got a working thing, the next thing to consider is reliability. Since if it can crash, it will, and it will in production. So there are two possibilities. First, if it crashes during master fork, if your script itself crashes for whatever reason, there's nothing actually you can do because you already tell the master to fork and it won't respond to you before it's ready. But luckily, since it only takes like 10 seconds, it should be fine. You just wait. If the new master itself crashes, which basically means your code fails to initialize or something, which means you wanted to fix your code instead of fixing this. Second possibility is if it crashes during worker transition. So what happens is if you run your push script again, it comes in and see two running masters with a bunch of workers separately. So what you could do is create a third one and moving workers from both. But what if that crashes as well? So you could create another one. So it turns out the master itself has overhead too. You cannot have too many of them. What we ended up doing is you just have an upper bound of how many master you have. And if all of them are filled, you just do a non-fork move to make up a free slot. And the idea here is this should happen very rarely, which should be fine. The last thing is we have to fight is the fact that forked processes actually carries over environment variable. In our case, we use this LD library path to tell the system where to load your dynamic libraries. So what happens is if you push a new version to these dependencies, the path here will change. And because you are using forked processes, you won't see this change. So the fix here is a little bit tricky, but the idea here is you reevaluate these environment variable and re-execute yourself. So re-executing is done by this privileged binary patch thing. So after that, what you do is you look at the environment variable, see whether the loading env is there. If it is there, you unset it so that next time you push, it will go through the if not env loading env branch again. So here's the final config we have. I don't expect you guys to read it. So just wanted to show you how many things that we wanted to add to the config. So the end result of this work is pretty awesome. First, you don't lose any capacity during push, which means you don't have to think about it. So instead of having your whole fleet running for a few minutes hot, what you see is like a little small CPU blip because there's still overhead, but it's tunable. Second is we actually enabled full parallelism with our deployment. You can just do 100%, no matter how many servers you have, and it will be fine as long as your code is fine. So now we're doing 70 deployments in average per day, and there was an engineering peak, I would call it, where there was one day our engineers worked really hard, and there was like 120 deployments on that day. Next thing is we get back the fast deployment during incidents, which means you don't have to worry about that. And on the other hand, you will be able to fix problems faster during your incidents. That's pretty much all I have. Thank you for listening, and I'm open to questions.
Any questions? We've got time for one question, maybe.
Hey, thanks for the talk. So in terms of when you're forking and updating the new code, is it simply a case of just updating the code on disk and then doing the fork, and that will pick up the new code and start with that?
So what we do in production is, in order for you to be able to revert, we put the new code in a place and we flip a symlink. Yeah, that's how. You could override your code, but it's usually dangerous, kind of, because you still have an old master running.
I think we're out of time.
Okay.
So thank you, Chenyang, for making the trip all the way from California to give the talk. It was very interesting. Please thank Chenyang Wu.